So we've discussed about elasticity and properties of matter in the last couple of lectures. Today we'll come to the last part of properties of matter chapter, which is surface tension and viscosity. So we'll see that the surface of a fluid acts like a thin layer of molecules, which is having a sort of elasticity and a tensional or a tension kind of force it can apply along the surface tangentially. And surface tension is a physical property that we attribute to that particular characteristic of liquid or fluid materials. So the surface of a liquid is a thin layer of molecules that exhibits elasticity. It behaves like an elastic membrane. That separates the body or volume of the liquid from its surrounding environment. So this elastic property is defined by its surface tension. Typically, we denote the surface tension with a symbol capital S or sometimes capital T also. So this elastic property of the surface arises out of or you can say is as a result of the nature of the cohesive forces. Cohesive forces are intermolecular attraction between same substance, in this case liquid molecules. At the surface. So the nature of these intermolecular attraction or these intermolecular interactions is responsible for the property of elasticity or surface tension. So we can visualize this type of cohesive forces that molecules at the surface experience, and how they are different from how the cohesive forces act on molecules which are within the volume of the liquid. From this diagram below, so now we visualize a molecule sitting at the surface over here. The cohesive forces that this particular molecule will experience will be like this, Whereas if you think of a molecule which is inside the volume of the liquid, it's experiencing cohesive forces from all directions in three-dimensional space. Whereas the ones on the surface, they're experiencing it only from half the volume around. Okay. So this is a comparison between a molecule at a surface and inside the body of the fluid. So this is the comparison of cohesive forces. So it is a difference in how the cohesive forces are in action at the surface versus inside the volume that creates that elasticity for that thin layer of molecules at the surface, which we denote by the quantity surface tension. So also we'll think of examples of surface tension related phenomena. Transverse waves propagate on fluid surfaces, like ocean waves, for example, waves that surfers use to propel themselves. So they are able to propagate due to the elastic nature of a surface. You can see surfaces tend to oscillate under the action of wind or even sound waves. These are all these phenomena that you observe in everyday life. They are all as a result of that property of surface tension, which gives the surface elasticity. If it were not the case, then transverse waves would not be propagating on a surface. There wouldn't be any elasticity to sustain the propagation of mechanical energy through a wave. Like that, there wouldn't be any elasticity to sustain oscillation of the surface under the action of wind or sound waves, etc. So all this is evidence that the surface does act like an elastic layer of material. Another example of the action of surface tension, see, is that insects walk on water surfaces without actually any portion of their body submerged. In this case, their body weight is balanced by the elastic forces that the surface is able to apply, because it is flexible, elastic in nature, like a thin rubber sheet or elastic membrane. Okay, now next point, we defined a surface as a thin layer of liquid molecules. So by thin, we mean that the thickness has the order of magnitude of a few times the molecular diameter. So it's that thin. Okay, now let's come to the physical definition of surface tension. So surface tension is a material property which can be measured in terms of two things. One of the things is in terms of force, but force per unit length. So surface tension for any liquid, the surface tension equals to the tangential force per unit length acting at its surface due to cohesive forces at the molecular level. So, for example, if you visualize, like let's say a cylindrical vessel containing liquid, and the surface of liquid in such a cylindrical vessel so that thin layer like a disc at the surface, that is what we call the surface. So if we now take the top view of the surface, then we can visualize that along the surface, tangential to it, if we draw an imaginary line of molecules, it's experiencing tangential force from either side. So if we just draw an imaginary line of molecules, this line of molecules at the surface will be experiencing forces which are tangential from either side like this. So that tangential force per unit length is the surface tension. So this surface tension is a material property of the liquid, and it is measured in newtons per meter, or sometimes it's measured more in millinewtons per meter. Is a more common unit. So this is the first definition of surface tension in terms of the physical property of force per unit length. We'll see there's a second definition also in terms of elastic energy, but the first definition is in terms of this elastic force or surface tensional force that acts tangential to the surface. So surface tension is measured in newtons per meter or millinewtons per meter because it is defined as the force per unit length that acts tangentially at the surface because of the cohesive interactions or the cohesive intermolecular forces that act at the surface. Okay, now the next property that we associate very closely with the surface is the surface's so-called surface energy, which is
Sir, can
basically
you
a
scroll up once?
didn't finish writing. Okay.
Done, sir. Done, sir.
Yeah, I'm waiting for somebody else also. Krish, you finished? Okay. Yeah, so the second property that we associate with the surface, apart from this force, tangential force acting per unit length, is something called the surface energy, which is basically a form of elastic potential energy of the surface. Okay, so we define the surface energy as the work done by an external agent to create the surface, because to create a surface, you need to stretch the molecules out against the internal conservative forces, which are the surface tensional forces or the cohesive forces. So in order to create the surface of liquid, a certain amount of work has to be done against those cohesive forces or against those surface tensional forces, and that work gets stored in the system as surface energy or as elastic potential energy. So the work done by an external agent against the surface tensional forces when a surface is created is its surface energy, which will denote with the symbol U of the surface. So the way to derive it now is to visualize a situation in which we are creating a surface of liquid where there was no surface to begin with, or at least no appreciable amount of surface to begin with. So imagine you're doing this experiment. You have two thin glass rods kept very close to each other, okay, and parallelly to each other, almost in contact. And you have a few droplets of some liquid which has high amount of surface tension, like glycerol or soap solution. The nature of the stearate ions in soap solution, long chain ions, enhances the surface tension because the cohesive forces. So something like soap solution has much more amount of surface tension compared to water. Okay. Or for that matter, glycerol or mercury, these are some of the materials which have the highest amount of surface tension. So there are small droplets of whatever liquid you're using, which are stuck together in the space between these two glass rods. So this is, let's say, soap solution. And these are two thin glass rods kept parallelly and very close to each other, and each of length L. Now, keeping one rod stationary, if the second one is slowly separated away from it, it creates a film of soap solution or a film of glycerol solution. So keeping the first rod fixed, the second one is slowly pulled away. It creates a thin film of soap solution. But in the process of creation of that soap solution film, and therefore the surfaces of that film, we'll have to do some work against the surface tensional force. And that work gets stored in the system. In this case, the surface of liquid as potential energy. So this is fixed. And the second one is being moved away very slowly. And as it is being moved away, you are stretching out a film of soap solution. So if you look at this side view, is the cross section of the two thin glass rods. You will see there's a film of liquid which is at least a few microns thick. So this is a film of liquid bounded by two surfaces. Okay, on each side. Surface 1, surface 2. Now, in order to keep moving this, we have to apply an external force which will balance this surface tensional force that acts like this. So on any sectional length DL, there's a surface tensional force which is surface tension into DL. So this net force due to surface tension this one becomes 2 times, if the soap solution has surface tension equal to S. So it becomes 2 times S into L. Why 2 times? Because there are two surfaces. So each surface parallelly applies force. So now, because the acceleration of the rod is tending to 0, it's moving very slowly. So the external force has to exactly balance this net force due to surface tension. So the external force's magnitude is 2 times SL. And if this has been moved through a distance x very slowly like this, so in the process, the work done by the external agent, which should have been by integration like this, constant force will just become x. So you can see that the surface energy, which is the work done by the external agent, stored in the surface as a potential energy, is surface tension multiplied by 2 times Lx. Now 2 times Lx is the total surface area, because there are two surfaces bounding the film of liquid. Okay. So we can see that surface energy is equal to surface tension multiplied by total surface area. So that gives us a second definition of surface tension. The surface tension of a material is the surface energy per unit surface area. This becomes the second definition of surface tension. So surface tension can be defined and measured on the basis of the two related physical phenomena. One is that there is tangential force per unit length acting at the surface, and the other is that there is any surface will store some amount of elastic potential energy, or what we call surface energy. So that surface energy per unit length is the same thing as the tangential force per unit length. So just make a note of this, people. Diti, the whole idea is that cohesive forces is what is responsible for surface tension. That elasticity, that flexibility of that layer of surface molecules comes because of the nature of the intermolecular attraction forces, which are cohesive in nature. Okay, so let's look at a typical problem based on this. So actually, before that, another important aspect of the property of any liquid surface related to surface tension is that because surface energy is directly proportional to surface area, any body or volume of liquid naturally takes a shape so as to minimize the surface area. Thereby, minimizing the surface energy. And minimum energy means maximum stability. So maximizing stability. So hence, in gravity-free space or a gravity-free environment, a volume of fluid naturally takes a perfectly spherical shape. Because the sphere has the property of minimum surface area for a given amount of volume. So in the absence of any other external force influencing the shape of a volume of liquid, like gravity, etc., the natural shape of a volume will always be a solid sphere, a spherical mass of liquid. So let's look at a numerical example problem based on that. Or before that, one more thing. So this is another reason why smaller droplets of liquid when brought together very close, almost in contact, tend to coagulate, or you can say coalesce, that is combined into a drop, because this minimizes the surface area. So now let's come to our numerical example problem. A spherical drop of liquid of radius, let's say 20 millimeters, and surface tension 200 millinewtons per meter, is split up into 1000 smaller identical spherical drops. So find the work done by the external agent, or you can say the energy supplied by the external agent to do so. Okay, so just try out this question quickly. Yeah, Yash, I think your answer is correct. So the first thing you can just send me a text with it is that what will be the radius of each of these smaller droplets? Like the original spherical drop has a radius of 20 millimeter. So what will be the radius of each of these smaller droplets? So let's say this was our original spherical drop. So this had a radius of 20 millimeters. So its surface energy would have been surface tension multiplied by 4 pi r square. So 200 millinewtons, so 10 raised power minus 3 into 4 pi into 20 into 10 raised power minus 3 square. This would have been the surface energy in joules. Okay. Now, the moment we break it into 1,000 smaller droplets, now obviously I can't draw 1,000, but 1,000 droplets, the total surface area would have increased. So each one has radius, let's say small r. So how much is the radius of each one? 1/100th of a millimeter. Yes. 1/100th of the original, I think. Yeah. Or is it 1/10th? 1/10th. Yeah, 1/10th will be correct. So basically, see what will happen, volume will be conserved. So the volume of fluid is 4 by 3 pi r cube. So that has to be equal to the volume of fluid now, which is 1,000 droplets each of this. Okay. So 4 by 3 pi capital R cube. So it's R by 10, you can see. So it will be 2 millimeters. So each of these droplets has a radius of capital R by 1,000 to the power 1 by 3. So each one now has a radius of 2 millimeters. And there are 1,000 such droplets. So the surface energy has increased from the initial value to now a value of surface tension into final total surface area. So that's this. So it is S into 1,000 into 4 pi into R by 10 whole square. So you can see it's become 10 times S into 4 pi R square. The final energy has become 10 times the initial energy. So the difference is 9 times the initial energy. And that will be our work done. So now connect this and this, and you'll see this is the difference in surface energy. So it's and now we can calculate this value. Okay, so that's how we work out this particular type of question. This is very common question in surface tension for competitive exams, mains and advanced. Okay. So this is the kind of value that I'm getting. You can check out. Yes, Tantrish, you got the same. Yes, I think you got the same in terms of pi. So if you convert, you'll get the same answer. Okay, so people, hope this question is clear to all of you. Now let's move on to the next aspect related to surface tension. Coming towards the end of this chapter, this portion of surface tension, and that is the concept of excess pressure inside a spherical drop. Now, this is also again a very important formula. So as we've discussed that if we have a volume of fluid or a body of fluid in a zero gravity environment, where it is not influenced by any other external forces like gravity or things like that, it will take a perfectly spherical shape. Now also you can visualize the surface, like a thin shell, like a skin, a spherical skin, which is separating the volume of the liquid from the environment outside. So if the environment outside is at a pressure of P naught, then the pressure of the liquid inside P is greater than the pressure outside by a certain pressure difference. So this pressure difference delta P is the excess pressure inside, and it is given by the formula. So if this particular spherical drop has a radius of r and the surface tension of the liquid is S, then this excess pressure is given by the formula 2S by R. Okay, we will quickly discuss the derivation of this formula also. But for you, more important is knowing the formula and learning to apply it in different situations, which we'll discuss. So let's take a quick look at the derivation of this formula. So we now visualize the free body diagram for half the surface, that is like a hemispherical part of the actual surface, not the whole body of liquid, but only the surface that is separating the volume of liquid inside from the external environment. So this is the FBD for half side of the spherical surface only. It's basically like a hemispherical shell made of liquid molecules. So this part of the surface, or this part of that shell, will experience force due to surface tension. That net force will be like this. So this is force due to surface tension. So that's like the intermolecular attractive force between half the surface on the left hand side and half the surface on the right hand side. So the surface on the left side is pulling the surface on the right side with surface tensional force. And that net force, you can see, will become surface tension of the liquid into the total circumference, that is 2 pi r. That's the first thing. Okay. Now the internal pressure of the liquid will be applying force vectors like this on the surface, radially outwards. And that will contribute towards a net force, let's say Fi, because of internal pressure. So how much that is, I'll come to in just a bit. But now the external pressure will also contribute towards an inward force like this. Let's say that's this. Okay. This is the net force due to external pressure. So just note down up to here, then we'll take it further from this point. Okay, so now let's understand how to calculate these two other forces, the external pressure force and the internal pressure force. So first of all, when you balance the forces here, you'll see this is an equilibrium. So the forces towards the left must balance the forces towards the right. Okay. So the force due to surface tension plus the force due to external pressure must balance the force due to internal pressure. Now, this force due to internal pressure, there's one way to calculate it, or the force due to external pressure for that matter. Now, separately, if we imagine a solid hemisphere, not a hollow hemispherical shell, but a solid hemisphere in a uniform external pressure field. Okay. So what will happen is that the force vectors from this side will be acting like this on it, and they will be creating this force that is the same as the F external for this diagram, and the force vectors on this surface from this side will be acting like this, and they will be creating a force, let's say like this. Okay, and the net force due to external pressure should be zero because the pressure is uniform. So F external prime has to balance F external. This is the force on the plane disk type surface, and this is the net force on the hemispherical side. So they have to balance each other. Now this F external prime is very simple. It is pressure into area. So it is P naught into pi r square. So therefore, this is also P naught into pi r square. And by a similar logic, the magnitude of the pressure due to the internal force, I mean the force due to the internal pressure will also become the internal pressure into pi r square. Just the direction is opposite because those vectors are acting radially outwards. You just go back to the free body diagram in the previous section, you'll understand. So these two forces are given by this magnitude. So let's start from this point. The equilibrium of this, let's start from that, and then
Done. Sir.
Yeah, I'm just scrolling down. Okay, so now we'll put these values of F external and F internal in the above equilibrium equation, and that will show us how the pressure difference or the excess pressure comes out to be 2S by capital R. Okay, so hope you're clear up to this point. So now going back to that equilibrium equation, so
Sir,
we
one
had,
minute.
okay, okay, so substituting in the above equilibrium equation, which was there, we had the force due to the internal pressure that was acting towards the right, balancing the force due to surface tension plus the force due to external pressure towards the left. So Fi minus F external had to balance the force due to surface tension. Now substitute these values. So you'll see that this is basically P minus P naught, or the excess pressure, into pi r square, and on the other side it's surface tension multiplied by 2 pi r. So you have the formula that P minus P naught, or delta P, the excess pressure, is 2s pi r.
Done.
Okay, now closely based on this concept or this formula rather is another fact. The excess pressure inside a spherical bubble. So there's a slight difference how this concept is applied between a bubble and a spherical drop. So bubble is basically a hollow shell of fluid. So it's like a like a spherical skin of fluid with air inside, or a film of liquid which is spherical in shape, a thin film. Okay, whereas spherical drop is like a solid sphere of fluid, solid spherical volume of fluid. So there are two different things in that respect. So when you're talking about a spherical bubble, just visualize it like this, but much thinner than what I've drawn. This is just for diagram purpose. So you have like a thin shell of liquid, like a soap bubble, for example. It's got air inside, and like a spherical shell, okay, or film of liquid, and its surface tension is equal to, let's say, S again. Okay. So if now, because it's thin, so we'll take the average radius instead of inner radius and outer radius. So if the external pressure is P naught and the pressure of the air inside is P, then in this case, what is happening? The pressure of the liquid inside is something else, this P prime. This is the pressure of the liquid in the film, inside that film. Okay. So first of all, P prime will be equal to P naught plus 2S by R. Okay. Because as you go from the convex to concave side across a spherical surface, okay, because there are two surfaces here. There's the outer surface and then there's the inner surface. Okay. So this is because of the pressure difference across the outer surface. That is your P prime minus P naught. That is equal to 2S by R. And the pressure of the air inside, that is P prime plus 2S by R again. Because again, the pressure difference across the inner surface, that is P minus P prime, that's also equal to 2S by R. Actually, the inner surface's radius is slightly smaller than the outer surface's radius, but we're taking both. So basically here we're taking R of the inner surface equal to R of the outer surface, equal to capital R. So now combining these two equations, you can see that P is equal to P naught plus 4S by R. So the excess pressure delta P inside a spherical bubble is given by the formula 4S by R. So just make a note of this concept also quickly. This area is 2 pi r square for the outer surface in the previous derivation. But see what is happening is that ultimately there is component algebra. On that spherical surface everywhere, the force due to external pressure is not acting along the horizontal line. It's acting like this. So with the resolution and all that, the net force comes out to be less than pressure into 2 pi r square. And how we calculate it is by using the clever concept that if you take a solid hemisphere, then the force due to pressure acting from this side has to balance the net force due to pressure acting from the other hemispherical side. So hope this point was clear during the derivation. I've just seen your question in the text message, so I'm explaining it now.
शेड्यूल है ना तब इधर शेड्यूल है ना तब फोन कर
Anyone had a question? Yes, was somebody asking a question? I didn't get it. Anyhow, so hope this formula is written out. So let's.
Sir, just a minute, please. Sir, please. Just a minute.
So example problem. Find the pressure inside a soap bubble. The radius of the soap bubble is, let's say, 4 millimeters, and surface tension is equal to, let's say, 180 millinewtons per meter, and atmospheric pressure is 5 pascals. Okay, so we want to find the pressure inside the soap bubble. So we have to just directly use this formula here. Okay. The internal pressure is equal to the external pressure plus the pressure difference, which will be 4s by r, because it's a bubble, okay, not a solid sphere. So 10 raised power 5 plus 4 times the surface tension, which is 180 into 10 raised power minus 3 divided by the radius, which is 4 into 10 raised power minus 3. So the change in pressure you can see is a very small amount compared to the atmospheric pressure. It's just 180 pascals. So the pressure inside is larger than the atmospheric pressure by just a factor of 180 pascals. So 180 you can see is, is 0.0018 into 10 raised power 5. So it becomes 1.0018 into 10 raised power 5 pascals. That's the internal pressure. So this type of direct formula based thing is there mostly. Okay. This chapter is not having too much weightage in JEE Advanced and neither in JEE Mains. At the most one question and most likely direct formula based or just a bit of concept. Anyhow, so that nearly completes surface tension. One more part of it we've discussed, which is about the capillary action or the capillary rise and the concept of contact angle. So we'll pick that up in the next lecture of properties of matter that we do, along with viscosity, which is the final property of fluids. And with that, we'll complete this section. But in the next lecture coming up this week, I will be taking only doubts. Specifically, I'll want to complete the doubts of fluid mechanics first of all, and then anything pending from before that, we will discuss that also. By before that, I mean it can be heat and thermodynamics, or it can be something from the other track of physics also, as may be the case. Okay.
Sir, you are having a doubt lecture.
Yes, this week the second lecture that we have, I think it is on Friday morning, if I'm not mistaken. Is it Friday or one of those days? Just look in your timetable.
Saturday morning.
I think it's a morning lecture. It's a 7:30 a.m.
Saturday
lecture.
morning.
Saturday morning. Okay, so that I will be taking doubts exclusively. Okay.
Okay.
Okay, people. That's it for today's session. People.
Excuse me, sir. Wait a minute. Sir?
Yes.
Sir, you meant that this chapter has less weightage in JEE Mains and Advanced, right?
Yeah, this entire section of properties of matter and particularly surface tension has very little weightage. But even elasticity, like the whole thing together also, elasticity, surface tension and viscosity, it has less weightage.
So then which has more weightage?
Mechanics has maximum weightage, then electromagnetism, that is electricity and magnetism, that part. And after that, it is heat and thermodynamics. Even waves has some weightage. Waves is the next section we'll be doing when we complete properties of matter, oscillations and waves. That is more weightage in comparison.
That's more weightage in comparison to.
Properties of matter.
Okay. Then the least is properties of matter.
Yeah.
Sir,
Yes.
sir, have you heard about antimatter?
Yes, Anuj, I've heard about antimatter, but today I will have to conclude the lecture here because I have something to attend to, some meeting to attend to.
Okay, sir.
You can drop me a message about antimatter. Any questions you have, I'll discuss with you later. Okay.
Okay, sir.
Okay, so that's it for today's session, people. Thanks for attending. Wish you all the best.
Bye, sir.
Bye, sir.
Bye.
Bye, sure.
Bye.